Now we continue with the loop current method. The loop current method is a systematic method of loop analysis given the following steps and illustrated using the figure below 9.9. So you can see the presentation is just a little different than the last setup. So again, methodically, 4 steps listed here. Although direction of an assigned loop current is arbitrary, we will assign current in the clockwise direction around each non-redundant closed loop for consistency. This may not be the actual current direction, again, as we saw before, but it doesn't matter. The number of loop current assignments must be sufficient to include current through all components in the circuit. So in this case, you can see we've got 2 loops, A and B, and current I sub A, I sub B. We indicate the voltage drop polarities, just like we did before, in each loop based on the assigned current directions. One thing to note here, I don't know if you've caught it before, but normally the side with the long plate on it is the positive side, and the short plate is the negative side. So you'll see that shown with that convention. If the polarity is the opposite, you'll see this whole symbol turn the other way. Okay, so step 3 says apply Kirchhoff's law around each closed loop. When more than one current loop passes through a component, include its voltage drop. So you can see here that through R2, we've got loops currents passing through in opposite directions through resistor R2. This results in one equation for each loop. Step 4 then says using substitution or determinants, solve the resulting equations for the loop currents. So a little more lengthy explanation. First, the loop currents I sub A and I sub B are assigned in the clockwise direction as shown. A loop current could be assigned around the outer perimeter of the circuit, but this would be redundant since I sub A and I sub B already pass through all components. So you can see there's no need to go around the outside and pick up only R1 and R3. Second, the polarities of the voltage drops across R1, 2, and 3 are shown based on the loop current directions. Okay, so they've assigned the polarities accordingly. Notice that I sub A and I sub B are in the opposite directions through R2 because R2 is common to both loops. So you can see if I put a down arrow here, I would have an up arrow here through R2. Therefore, 2 voltage polarities are indicated. In reality, R2 current cannot be separated into 2 parts. But remember that the loop currents are basically mathematical quantities used for analysis purposes. So you can see we've got positive, negative, negative, positive because of the direction of current flow that they've chosen. The polarities of the fixed sources voltage sources are fixed and are not affected by the current assignments. So step 3, we apply Kirchhoff's voltage law to the 2 loops, resulting in the 2 equations. So we're going to write the equations R1 I sub A, R2 I sub A minus I sub B, because the current's moving in opposite directions there, is equal to voltage source 1. And we write another loop current equation for the loop B. Notice that I sub A is positive in loop A, I sub B is positive in loop B. Okay. 4. The like terms in the equations are combined and rearranged into standard form for convenient solution so that they have the same position in each equation. That is, the current I sub A term is first and the current I sub B term is second. The equations are rearranged into the following form. Once the loop currents are evaluated, all the branch currents can be determined. So you can see we've written them. We've written them out here. In this case, we've got I sub A with the addition of the 2 resistors, I sub B with R2, and we've done the same thing with loop B. Notice that in the loop current method, only 2 equations are required for the same circuit that required 3 equations in the branch current method. The last 2 equations developed in step 4 follow a form to make loop analysis easier. Referring to these last two equations, notice that for loop A, the total resistance in the loop is R1 plus R2 and is multiplied by current I sub A, its loop current. Also, in loop A equation, the resistance common to both loops, R2, is multiplied by the other loop current, I sub B, and subtracted from the first term. The same form is seen in the loop B equation, except that the terms have been rearranged. From these observations, a concise rule for applying steps 1 through 4 are as follows. Sum of the resistors in the loop times the loop current minus each resistor common to both loops times the associated adjacent loop current equals the voltage source in the loop. Okay, so we've said a lot there, a lot to digest. Go back through that and try to get a better idea of what this is all about. We've got an example in the next video that hopefully will drive the point home.